welcome to the lecture in the series of Advanced Material and Construction. And today we're going to talk about material classifications and characterization. So we have this whole bunch of materials around it, just this variety keeps going and expanding. And I would like to have an idea of how do we look, how do we categorize these materials, and how do we approach this diversity. And a first look could be through the engineering type of approach, which classifies actually three main categories of materials. We have metal and alloys, we have polymers, and we have ceramics and glass. That's the materials that we use for our construction traditionally. And in the middle, we have the composites, which actually make this composition between two elements to generate a third type of material, third family of material that sits in between. When we take this classification into architectural books, for example, like this book of Fernandez of Material Architecture, we see that we have a deployment of each of these categories, and it adds also the natural material as a category that is useful for us as architects to think about. So we will have there the wood, for example, that is very important, and other natural fibers that comes into place. I like very much this diagram of Ashby mapping these families, these same categories of material over time, and it starts in 10,000 before Christ, so really almost prehistory, where we see the evolution of all these materials existing there, and the way man is evolving and their relative importance in our lives, in our usage, as man goes on and develops its material reality around. For example, interesting to see the composite materials which are there from the first place, because this is actually the brick, right? We take a mineral material, the mud, the earth, the ceramic that is around, and we combine it with fiber, natural fiber, which is the straw, and then you get the brick, which is the very first element or the very first composite material that man is making up for an architectural creation. And you see the relative importance evolving. So we have the steel, which the age of steel coming into place, taking a huge importance all the way towards the 20th century, and then comes the age of polymers and the current developments that we see today. So following this very basic categorization of engineering materials that we see here also over history, if we add a chemical composition aspect to this categorization, we get here a few more groups, as we see here in this mapping. Still in the center we have the hybrids, as we had composite before, just a different naming. But you see the separation, for example, between polymers and elastomers, or between glass and ceramics. So we will have elastomers. Due to their chemical linkage, they are very elastic, as opposed to the polymers, thermoset or thermoplastic, which are stiff and regarded as organic solids. And another example would be the ceramics, categorized as inorganic solids, high stiffness, whereas glass, quite similar but still amorphous solid, so it's very different in chemical composition, with all the high portion of silica in the composition of the glasses, which make it transparent and corrosion resistant. Very different from the ceramics. And on the basis of this chemical composition, we see here a development through taxonomy. Taxonomy is a hierarchical distribution of the information, like a tree structure if you want. Actually, taxonomy comes from the world of biology. So the father of modern taxonomy is considered to be Carl Linnaeus, 18th century, and he writes this Systema Natura, trying to understand the system behind nature around, and he establishes this idea that the living world is comprised of kingdoms. So he has two kingdoms in the first place, and over time it's developed. So Ernst Haeckel is developing it to three kingdoms. So we have plants, we have the animals, and we have the protists. And actually this evolution goes on and on till today. We have system of 5, 6, and even 8 different kingdoms. So if we take it into our material, we have our material families, the kingdom of material. Then inside it there are families, classes within the family. So for example, here we have the metals, and within the metals we have ferrous and non-ferrous metals that are displayed, and then the members would be the density of the elements and their attribution, and this is how we can get a full mapping of our options or available possibilities. And this system of classification of materials, upon that we will add the classification of processes, because upon the raw material we have a strategy to be chosen of shaping, joining, and surface treatment that will be applied to the suitable material for the suitable application. So we see here, for example, within the kingdom of processes, we can take shaping, and within that we can choose, for example, the class of molding, and that we can have injection molding, and we have a lot of attribute within the injection molding to be chosen, so that we get the specification of the end process or product that we wish to achieve. I like very much this graphic representation of material taxonomy. So if you see here material, product, and process that we've just mentioned with some families and their icons. So starting from the material, you have the metals, we have the ceramics and the natural polymers as it is called here. Above this we have the product, or the way we obtain this material. Is it a rod, is it a sheet, is it a fluid? And the process that we apply upon, as we mentioned before, is it joining, is it printing? And to that we add a whole other set of taxonomies. So we have the type of connection, the type of finishing, and even the structural system in which we apply this material. In material science, they introduce the very interesting concept of the material tetrahedron. So this is a triangular pyramid involving processing, properties, performance, and structures. All these parameters, these criteria, and the interplay between those result in characterization of the desired or the appropriate material for a specific usage. And upon this classical structure, we have a suggestion, reimagining the material tetrahedron, where the pyramid is transformed into a rectangular pyramid. And this time we have what is added is actually the basis of all this, and that's sustainability or criticality of the material. And that's the first time that we have the factor of environment and sustainability coming into place, and that transform actually or gives a whole different context to the whole equation. Demonstrating this new revisited material tetrahedron with rectangular base is this quote: "For every scientific or engineering action, there is an equal and opposite social reaction." This is furthermore interesting because it comes from a businessman invested in the aerospace industry, actually the chairman of Lockheed Martin's, one of the heaviest industry that there is, usually not taking those parameters into consideration. These two aspects of properties of a material are here classified by Fernandez into two property families. And we have one family of intrinsic properties and the other of extrinsic properties. What does it mean? Intrinsic is inherent properties of the material, regardless of where or when or what you're doing with it. It could be its strength, mechanical properties, chemical properties, thermal, etc., of the material itself. Another category or type of properties is the extrinsic, and this is already dependent with application, context, time, and place. It could be the price, it could be the environmental effect of the usage of this material. And when we think about a material and the way we would like to apply it in architecture, we need to be conscious of these sets, both sets of properties and the way they interrelate. Let's have a look at concrete as an example and try to understand its position today through both intrinsic and extrinsic properties. So if we look at the intrinsic properties, we have here density mapped versus compressive strength. So we understand that the material is medium in its compressive strength, and it is rather heavy. It's placed in the middle. So performance, I would say medium in that respect. In parallel, we see that thermal conductivity, it's rather conductive. It's not isolating as wood or other materials. And however, we see below that its usage in construction is almost complete. It's almost all of the percentage. Most of this circle is orange. How could that be? Why do we use concrete so much? Well, we have the extrinsic properties that would maybe shed a light on that, because we see that it's very cheap. You see it's positioned here on the left, bottom left on the graph, and relatively low on the embodied energy. However, since its usage is so total in the construction world, it still is accountable, responsible for the majority of the embodied energy in the construction activity today. And this is rather significant. As an example of intrinsic property, I would like to go a little bit deeper into mechanical properties and how these are important for us to understand the best way of service of these materials in architecture. So we have the terminologies of strength, elasticity, ductility, toughness, and hardness. I'm sure you've heard all these before, and these might a little be confusing, the difference between all of those. So let's have a little look on some of these. I would recommend the series of videos of The Efficient Engineer. It is on YouTube, and it makes this whole topic very accessible and easy to understand. So let's start with stress, for example. Stress would be the force that we apply per unit area of the element. So this force could be tension or compression, bending or torsion, but it has to be on a unit area. For example, Newton per square meter is a unit that we would measure, or Pascal, megapascal, etc. The strength of our material will be the point above which our material cannot withstand the stress, so above which we have a failure.
Stress and strain are fundamental concepts that are used to describe how a body responds to external loads. In this video, we'll explore these concepts using the simple example of a loaded bar. Here we have a solid metal bar that is loaded by two equal but opposite forces. We refer to this as uniaxial loading, because all of the applied loads are acting along the same axis. The two forces are pulling the bar, causing it to stretch. Internal forces will develop within the bar to resist these applied forces. We can expose these internal forces by making an imaginary cut through the bar. I chose to remove the right side of the bar, but I could have removed the left side instead. For any imaginary cut like this one, the internal forces develop in such a way that equilibrium will be maintained. In this case, the effect of the internal forces acting on the cross-section created by our cut will be equal to the effect of the applied external force. Strain is a quantity that describes the deformations that occur within a body. If we fix our bar at one end and apply a force to the other end, the force will cause the bar to deform. The normal strain within our bar associated with this deformation can be calculated as the change in length of the bar delta L divided by the original length L. Strain is a non-dimensional quantity and is often expressed as a percentage. Normal strains can be tensile or compressive. I mentioned earlier that the concepts of stress and strain are closely linked. The relationship between the two can be described using a stress-strain diagram. Stress-strain diagrams are different for different materials. We can obtain the diagram for a specific material by performing a tensile test. This involves applying a known force to a test piece and measuring the stress and strain in the test piece as the applied force is increased. Stress-strain diagrams for ductile materials like this one show that there is an initial region for low strain values where the relationship between stress and strain is linear. Deformations occurring in this region are fully reversed when the load is removed, and so are said to be elastic. This linear relationship between stress and strain is defined by Hooke's law. The ratio between stress and strain is called Young's modulus, which is an important material property. Hooke's law usually only applies for small strains. For larger strains, the relationship between stress and strain is no longer linear. Deformations are not reversed when the load is removed, and we have permanent plastic deformation. You can learn more about stress-strain curves in my videos about Young's modulus and about material strength, ductility, and toughness.
So we see here the Ashby map where we have material family distributed in density versus strength. So how heavy is the material and what would be the point of failure of this material. Important to note, all material families are mapped where stress applied is in tension. Just ceramics material family is mapped in compression because this material is very brittle and his strength is under compression. So that's why it's dashed in this mapping. And we see what is quite intuitive to us. We know that metals are rather heavy, but they are a high point of failure. And natural materials like wood, they are much lighter. So on the left side of the graph, but they would be also on the lower part, meaning their point of failure, or they would be more weak. Their point of failure is going to be lower. So above this interest of in the strength of the material, so at one point the material will break, we are also interested on the behavior of this material when stress is applied. So we see these graphs on the left. You see the dynamic, or what is happening as we apply the stress on the material. What is the deformation that we get? And that would be the difference between a brittle material and a ductile material, ceramics and metals if you want. And this is actually the stiffness of the material. So let's have a look at this graph. We see different types of materials, and strain is mapped with stress. So strain is the deformation that we get in the material when we apply a force, and the type of deformation we get. So we can have, we can guess what type of materials we have. We have the lower curve. This is a material where we have very little stress applied, and we have a long deformation, but it doesn't break. And maybe the other area of the graph is this material on the left, where we see that a very high stress is applied, nothing happens, and then it breaks at once, and this is a very brittle material. So here you see actually the material families that are mapped. So we will have the brittle ceramics on the upper left, and we have elastic viscous material on the bottom right. And in the middle, we have metal materials that are ductile. That means that they have a rather high point of failure, and in the middle, they will have some plastic deformation. So within this characteristic of stiffness, characterized with the coefficient of a Young's modulus, we actually have a whole phases of behavior of the material within this stress applied. And this would characterize elastic deformation, plastic deformation, and also the toughness of material. Let's see this video.
In this video, we're going to take a closer look at strength, ductility, and toughness, three very important material properties. Let's get started. Strength is a measure of the stress a material can withstand. Two different values are typically used to define the strength of a material: the ultimate strength and the yield strength. Let's define them by taking a look at the stress-strain curve obtained from a tensile test. The ultimate tensile strength of a material is defined as the maximum stress, which is reached during the tensile test, corresponding to this point on the stress-strain curve. It is the maximum stress the material can withstand during a tensile test. The yield strength is defined as the stress at which a material begins to deform plastically. Stressing a material beyond its yield strength will result in permanent deformation after the load is removed. Many structures and components are designed to ensure that they only deform elastically. This makes the yield strength a commonly used criterion for defining failure in engineering design codes. It is possible for failure to occur at stress levels well below the yield strength if the applied load varies with time. This failure mode is called fatigue, and I will cover it in a separate video. For some materials, the transition from elastic to plastic deformation is not clearly defined. In these cases, the yield strength can be defined using the 0.2% offset method. This involves drawing a line with the slope equal to Young's modulus and shifting it 0.2% to the right on the stress-strain curve. So far, we have only discussed strengths in the tensile direction. But what about the compressive direction? For ductile materials like mild steel, the yield and ultimate strengths are very similar in the tensile and the compressive directions. Tensile tests are usually easier to carry out than compression tests, and so compression tests aren't often performed for these materials. For brittle materials like concrete and ceramics, however, the material strength is much larger in compression than in tension. I will talk about why this is the case later on in the video. First, let's look at some examples of strength values for a few different materials. Tensile yield strengths are shown for ductile materials, and ultimate compressive strengths are shown for brittle materials. Graphene is the strongest material to have ever been tested. It is a two-dimensional material made up of a single layer of carbon atoms arranged in a hexagonal lattice and linked by strong covalent bonds. Defect-free graphene has an ultimate tensile strength of up to 130 gigapascals, or 19,000 ksi. I've mentioned material ductility a few times in this video, so now is probably a good time to define it properly. Ductility is a measure of the ability of a material to deform plastically before fracture. Let's return to our stress-strain curve. Materials which undergo large amounts of plastic deformation before they break are called ductile materials. These materials fracture at very large strains. Mild steel and gold are examples of very ductile materials. Materials which fracture at very low strains with little to no plastic deformation are said to be brittle. Glass and ceramics like porcelain are examples of brittle materials. Because they don't deform plastically, the concept of yield strength is irrelevant for brittle materials. There is no defined transition point between ductile and brittle behavior. Typically, a material which has a strain at fracture of less than 5% is considered to be brittle. Now that we have covered what ductile and brittle materials are, let's return to the question of why brittle materials are much stronger in compression than in tension. There are two factors at play. The first factor is that tensile loads tend to encourage the formation and propagation of cracks, whereas compressive loads do not, as illustrated here. The second factor is that in brittle materials, very little or no plastic deformation occurs to redistribute stresses at existing flaws. This means that large stress concentrations build up at the crack tip, resulting in fracture. In ductile materials, plastic deformation occurs, which relieves these localized stresses. Ductility can be dependent on temperature. A lot of different types of steel, for example, are ductile at room temperature, but become brittle when the temperature drops to below the ductile to brittle transition temperature. This transition temperature is an important design consideration, because ductile failure is normally preferred to brittle failure. One very famous example of brittle failure is the Titanic. The icy waters of the North Atlantic are thought to have caused the steel of the ship's hull to drop below its ductile to brittle transition temperature, resulting in catastrophic brittle fracture. Toughness is the ability of a material to absorb energy up to fracture. It can be calculated as the area under the stress-strain curve. If the area under the stress-strain curve is large, the material will have high toughness, and so will be able to absorb a large amount of energy before fracturing. For a material to have high toughness, it should have a good balance of both ductility and strength. Low-strength materials and brittle materials tend to have low toughness. A related property is resilience, which is the ability of a material to absorb energy when deforming elastically. It corresponds to the area under the stress-strain curve, but only within the elastic region. Materials with high resilience are well suited for applications where plastic deformation is to be avoided. To summarize, the yield strength of a material defines the stress at which it begins to deform plastically. The ultimate tensile strength defines the maximum stress which is reached during the tensile test. Ductility is a measure of the ability of a material to deform plastically. Toughness is a measure of the ability of a material to absorb energy up until fracture. And resilience is a measure of the ability of a material to absorb energy while deforming elastically.
So we have these three a bit confusing concepts, let's say, introduced. On one hand, the strength of the material. On the other hand, we have the ductility. So once stress is applied, what kind of plastic deformation, what is the amount of deformation, elastic and plastic deformation that we have in the material? And finally, the toughness, or how much energy is required to actually bring the material into failure. And that's this area under the graph that we saw before. So in this Ashby map again, you see that although ceramic are very high up in their strengths, they are very brittle, meaning we need just a little bit of energy to invest to break those material, and that's why we see those material are higher up in the left. Whereas woods or composite, as you see in the diagrams on the right, you see that wood is spreading over a large area in the graph, probably thanks to the directionality of fibers. We'll get to that later on, but their application depends very much on the orientation of the fiber and also on the type of wood. So you would have some that are more brittle than others, or less tough than others, I would say. And composite material, which actually we get somehow best of both worlds, because we get not only high strength, but also high toughness of the material and also a good ductility of these materials. So that was a quick look, very superficial, into mechanical properties, and just to say, as you have this whole family of properties, you have also thermal properties, for example, and the intrinsic properties of materials. Here we have a mapping of thermal conductivity versus the expansion. So while we would like our material to be isolating, for example, in architecture, so less thermal conductivity, we would also like them not to expand, right? Once we have a high expansion of materials, for example, in metals, then we have some problems and cracks occurring maybe in our building. So we would like stable material that don't have a large coefficient of expansion, so they would be rather lower on the graph, and at the same time would like them to be also not conductive, so we have isolation. That would be measured in a unit length, millimeters, per time unit, per hour or day, and a degree. So if we rise the temperature in 1 degree, how much expansion, how much our material will get larger. So you understand that each of this intrinsic property is crucial to the understanding of the behavior of your material and suitability for your application. But, as says Fernandez, in architectural design, simply applying some knowledge of material properties and classification is not enough to produce effective and responsible building system. Material properties and their collective behavior can only be fully assessed for a particular application when considered within the macroscopic behavior of the entire system itself. And Fernandez goes and classifies actually our building application into 4 different systems within the building. So we have superstructure, enclosure, interior, and building services. Superstructure, we understand actually that's the structural shell of our building, and its main role is to transmit the loads to the ground, forces applied over our building, the loads applied to the ground. And it has also to resist to the external forces. Then we have the enclosure. So this is the barrier, and its role is to control and transfer the external condition that we have and balance it with the internal conditions that we wish to have. It protects us, it isolates us, and permeates whatever we want to permeate into the building. Then the two other systems are the interior system that needs to delineate the interior spaces mainly, and provide some acoustic separation, and the building services, all the services that actually their role is to supply us with the comfort of heat, cooling, ventilation, water supply, etc. And it's interesting to see within the building system of Fernandez how materials are applied and what are the relative importance of each of the families of material in each and every system. And you also have subcategories, for example, timber structure, metal structure, and concrete structure for the superstructures first category, and the relative importance of all the materials and how they take part in that, and what we could wish for in the future if we had different consideration, for example, environmental consideration that comes into play. So within this field of extrinsic properties that should be taken into consideration related to material, we have material depletion. If you remember the square-based pyramid of sustainability or criticality, so that means actually how critical is the use or the existence of this material. And this graphic shows very clearly what will happen if we continue using at the same rate, or if rate continues to grow, that's the thicker lines, of the material over time. And with this title, How Much Is Left for Me, you understand that if we continue using some of the material over time, there will be no resources left. And EU is highly concerned of the condition of raw material, and there is this raw material initiative. I recommend to have a look at it over the web, and it actually talks about the criticality of raw material as it is today and as it is evolving. And EU is very much concerned of the raw materials and how they are used with our technologies, because there are some technologies that we promote that we are highly interested in, and you see them on the right. So basically these technologies, clean technologies, for example, that could be electric cars with e-mobility, information technologies, of course, and aerospace and defense, with the sub-technologies of robotics, data storage, and so on. So even with renewable energy, e-mobility, things that we encourage, we understand that these technologies require some raw materials that are in a critical state. So this graphic shows the thickness of the material is the amount used, and the shade of the line is the criticality. Maybe even more easy to understand, we have these graphics that show actually the trends of the material. You have the arrows going up and down. So we have these two columns with the trend going up and down. You see the supply risk on the left, and then the economic importance of the material. So in addition to the trend, you have also the shade that exemplifies the criticality of each and every material. And for each material, you can get into a dashboard that is full of information if you are interested in. So if we have a look at cobalt, for example, we see that 64% of its production of the raw material, extraction of the raw material actually, is located in one place. And not only it's in one place, but it's in Africa. So you can understand that this generates a lot of instability and economical, geopolitical potential problems. And this is of high concern. So here you see a mapping of different raw materials that are highly concentrated on one region, and this is actually a high risk. So if you map the economic importance of the materials and the supply risk, you get this region, which is considered a critical region. All of these materials are positioned in a critical region where we are concerned because they are very important economically, and they actually are in a supply risk. And you see cobalt is very critical here on the far right. And why do we need cobalt at all? Well, actually, we need cobalt more and more because cobalt is one of the primary elements that constitute the batteries for our electric car. So while we are promoting the development and usage of electric car for environmental reasons, on the other hand, we also have the effect of the criticality of the material where it's produced from, and the fact that it's all concentrated in a very problematic region. And this conflict is actually non-solvable, and that's something we have to be highly aware of when promoting a usage of some technology, even if it's a clean and green energy. And you see the cobalt rise and surge over the years in this graph, and this explains very well the development of e-mobility on one hand, but on the other hand also the criticality of this material of the cobalt. Another example that demonstrates strongly this connection between the criticality of raw material and international geopolitics is palladium. That's a heavy metal. And not only the resources, the natural resources are concentrated mostly in one place, but also its extraction, and that is in Russia. Now, with the war that has been going on, the invasion in Ukraine since early 2022, we see the rise of palladium, of the prices and the criticality that is developing, and the alarm of raw materials reaching record high due to this war between Russia and Ukraine. And you see palladium at the top presenting a very critical image of the availability of these resources worldwide as they are held in one localized place. To conclude, let's have a look at the global material usage over time from the early 20th century to today, categorized by resource type. And we see that construction minerals, so basically related to architecture and construction, is in the deepest rise maybe amongst all, and this is highly critical. As architects, as part of the construction industry, we are accountable for 39% of the global emission today. So it is our duty and our obligation as professionals to see how we get these figures lower. So these figures are comprised of the construction of the building itself and its operation, and all of which is heavily influenced by the materials we use. And this means that we get into action at this point as architects. And getting into action, that is first to understand what's the consequences of our choices. So I strongly recommend you to go and look at this material pyramid, a very accessible way to understand in a relative comparison the influence or the importance of materials we use in this architectural context. And in this site, you first have to choose the parameter with regards to which you want to assess the material. So it could be global warming, but it could be also ozone depletion or acidification. And in parallel, the way by which you use the material in your project, should it be assessed for roof cladding, insulation, or facade, for example. So if we take here insulation, and the three parameters, global warming, ozone depletion, and acidification, you see a very different organization each time of the materials over the pyramid. And EPDM foil, for example, you all know this material for insulation. So in global warming, it's at the very top, whereas in other parameters, it's medium in acidification, and on a lower part of ozone depletion, other materials such as EPS foam have a much better positioning with quite constant positioning at the lower pyramid that is more beneficial to use in all parameters. We have to remember that the materials that we use is just one fragment of our assessment of the influence or the global footprint that our building is going to have on our environment. And that's actually the life cycle assessment. So we are assessing our building throughout a cycle, starting from the extraction of raw materials and their processing into construction process, of course, transportation of all these elements, and then the usage, the life service of the material, and its end of life, how long it's going to last, and once it's not useful anymore, what happens with the building itself. And each and every of these steps is comprised from a lot of parameters of evaluation, most of them done numerically in a very rigorous way. So we could aim to evaluate our process from cradle to gate. That is from the moment we extract raw materials to the point that it leaves the factory towards implementation, whatever. So that's the minimal assessment, I would say, to the most comprehensive assessment, which is the cradle to cradle, not only from the creation of the material and its service and end of life as cradle to grave, but also the way it's reused, recycled, and reinterpreted. So these assessments, they actually look something like that. So that's an example of an LCA, a life cycle assessment of fiber-reinforced polymers towards glass. So this life cycle assessment is a comparison between FRP, composite materials of fiberglass, with regards to treated glass. And these panels are assessed to very different parameters. And you see that, for example, whilst the embedded energy in the production of fiberglass might be higher, the amount of material is used is significantly lower. And that's why it's very important to have a very comprehensive and complex assessment of all parameters of the building. And it looks something like that. So you have different categories and a scoring each. And the picture that you get is actually the comparative picture of all of this combined together for your specific application. As architects, as designers, we have the obligation to get a complex picture. There is no good or bad material. It is always with relation to the way we use it, where we use it, and the parameters that we take into account, as you see, for example, in this detailing of Healthy Material Lab. And we all need to aim to design a healthier future, and it is also in our hand by the materials we use. Thank you very much.